In dynamical systems theory, world evolution follows a precise mathematical logic known as a Markov decision process. An action is taken, which alters an underlying latent state. That latent state then emits what we actually see, the visual observation. Modern video generation models attempt to shortcut this entirely. Instead of calculating that hidden state, they rely on mapping actions directly to pixel-level changes, based purely on a text prompt. Without an explicit state anchoring the scene, the model relies on surface-level visual patterns. Over a long time horizon, tiny pixel errors accumulate, physics begin to drift, and the model eventually hallucinates, losing track of where objects are or what condition they are in. To build a truly generative action role-playing game, painting plausible pixels is insufficient. The model must compute the underlying physical consistency of the world before it renders a single frame. Consider the act of firing a weapon. The action shoot alters a hidden state, the remaining ammunition count. If a world model only understands the visual pairing of pulling a trigger and a muzzle flash, it will continue rendering fire and projectiles even when the gun is completely empty, entirely missing the underlying mechanical click. Solving this requires a substantial engineering pivot. WildWorld is the solution designed to explicitly decouple the underlying state from the visual observation in the training data. The dataset consists of over 108 million clean, annotated frames captured directly from the AAA action role-playing game Monster Hunter Wilds. Within those 108 million frames, the researchers cataloged an extensive catalog of over 450 distinct player and NPC actions, from evasive rolls to heavy attacks, all perfectly synchronized with their explicit per-frame world states. By capturing both the mathematical reality and the visual output simultaneously, WildWorld provides the necessary bridge to evolve from simple video generation to true interactive world modeling. To capture this dual reality, the research team engineered a custom data acquisition platform that splits the game's architecture in two. They isolated the game engine, which continuously calculates the true mathematical state, from the rendering pipeline, which simply draws the visuals. On the rendering side, the pipeline records the raw visual output. They deliberately disabled late-stage shaders to strip away all heads-up display elements, producing clean, unobstructed gameplay frames. Simultaneously, the engine side records the hidden mathematical data. It tracks exact 3D spatial trajectories, velocities, and the precise skeletal poses of both the player and the monsters. The density of this capture is extreme. For every single frame of those 108 million, the platform logs exactly 119 columns of data. This includes XYZ locations, rotational quaternions, camera extrinsics, and internal attributes like health pools and cooldown statistics. This paired architecture means every visual observation is firmly anchored to its true latent state, providing a mathematically perfect ground truth for machine learning models. Capturing 108 million diverse, high-fidelity frames of action combat presents an immediate logistical wall. Human gameplay cannot physically scale to this level of output. To achieve scale without human intervention, the team utilized the game's native behavior tree AI. They automated teams of NPC companions and unleashed them into unscripted, highly stochastic combat scenarios against large monsters. Because AI-controlled combat can result in chaotic viewing angles, they co-opted the engine's built-in target lock camera system. This ensured the framing remained stable and visually coherent while the automated characters fought. The resulting raw data then passed through a rigorous algorithmic filtering pipeline. Crucially, a temporal continuity filter analyzed the exact timestamps of the state records, immediately dropping any sequence where the frame gap exceeded 50 milliseconds to eliminate microstutters. They applied additional heuristics to discard frames where the camera was occluded by level geometry, or where extreme lighting conditions caused prolonged overexposure or darkness. Relying on behavior tree automation and aggressive algorithmic filtering generated a dataset that is both massive in its scale and chemically pure for training diffusion models. The final layer of the WildWorld pipeline applies text-based metadata, creating hierarchical captions that translate the raw telemetry into language that text-to-video models can process. They fed sampled frames into the Qwen3VL vision language model. To prevent the model from hallucinating the context, they hard-coded the exact state metadata directly into the prompt as a factual anchor. This forces the caption to include hyper-granular details. The resulting text explicitly defines the player type ID, the exact weapon ID in use, precise fractional HP values down to the decimal, and absolute rotational quaternions. These charts display the dataset's statistical composition. A pie chart shows a 66 to 34% split between combat and traversal. Beside it, a bar chart reveals a long-tailed distribution across the top 150 actions, ensuring rare, complex interactions are captured alongside common movements. This multimodal annotation takes unstructured, chaotic gameplay and turns it into a highly structured pedagogical tool, explicitly teaching diffusion models the rules of a physical environment. With the data secured, the researchers turn to how we actually test these models, challenging the current industry standard by exposing what we can call the WildBench illusion. Traditional evaluation pipelines rely heavily on metrics like motion smoothness and aesthetic quality, but modern generation models are already saturating these tests, regularly scoring over 95% across the board. A high aesthetic score simply means the video looks pretty. It is entirely useless for determining if a model adheres to physical laws or accurately responding to a user's control inputs over time. To fix this, the team introduced WildBench. It is a purpose-built evaluation framework derived from the WildWorld Dataset, designed strictly to test interactive fidelity rather than surface-level beauty. WildBench benchmarks the model's ability to act like a real world. This standard identifies failures in physics and logic that aesthetic scores have completely ignored. To answer that, WildBench relies on two critical new metrics: action following to track input accuracy, and state alignment to measure physical consistency. For state alignment, the framework uses an algorithm called TapNext to track 2D skeletal trajectories directly in the generated video, checking those output coordinates against the mathematically perfect ground truth recorded from the game engine. This table breaks down the resulting paradox. Looking at a baseline model like WAN 2.2, it scores near perfect on visual dynamic degree, but looking at the actual physics, it fails drastically, scoring a mere 11.29 on state alignment. However, when models are explicitly fine-tuned using WildWorld state data, the physical metrics surge. Models conditioned on camera and skeletal data saw massive improvements, nearly doubling their accuracy in following actions and aligning states. But the data reveals a severe trade-off. The models that utilized explicit state conditioning to improve their physics suffered a noticeable corresponding drop in raw image quality and aesthetic scores. The experimental results confirm that the field is currently deadlocked in a zero-sum game. Right now, architectures are forced to prioritize either strict physical accuracy or high-fidelity pixel aesthetics. They struggle to achieve both simultaneously. Achieving true, long-horizon interactive world models requires an explicit state architecture, moving past the brute force generation of isolated pixels. The 108 million annotated frames inside the WildWorld dataset provide the foundational data required for researchers to finally break through this aesthetic accuracy bottleneck. To dive deeper into the code and architecture driving this research, head over to the Learn by Doing with Steven YouTube channel. For long-form discussions breaking down the raw data behind these breakthroughs, search for the Steven Data Talk podcast, available on YouTube Music and Spotify.